we're going to be learning about gas laws. This is our last unit for the year. Woohoo! Okay, so some elements exist at gases at normal standard temperature and pressure, and these elements are listed in blue on this periodic table of the elements. Look at my periodic table of the elements on the wall. You see that they're listed in red. What do all of the elements that are gases at standard conditions have in common? They are nonmetals. Good job. So nonmetals, notice that they are also have something else similar between all of them. Thank you. If you notice on the right-hand side there, all of those in blue on the last column, who remembers what those kind of gases are called? Yes. Noble gases. And then the other ones that aren't noble gases are our diatomic elements. You guys remember that? What does diatomic mean? Caleb? They come in pairs of two. So what that means, let's remind ourselves, those are our high 7 elements. High for hydrogen, then go over to number 7, and it'll make a number 7 on the periodic table of the elements. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are our 7 diatomic elements. Makes a 7, starts with number 7. There's also 7 of them. So the other gases that are elemental are diatomic gases. Here's kind of a list of them. Notice that our diatomic elements that are on there are molecular. That means that they are a molecule bonded through shared electrons. And then let's go over to the compounds there. Notice we have at the top hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. Now remember when we learned about acids, we called those hydrofluoric, hydrochloric, hydrobromic, and hydroiodic. Do you remember learning how to name those? Those are naming them as acids, but here we did not name them as acids. Does anybody remember what it means to be an acid? Simplest definition, Arrhenius definition. Provides H+ in solution. So that's the difference between these gases, look at these tiny little gases, and if they are dissolved in water. So the difference between hydrogen fluoride and hydrofluoric acid is that hydrofluoric acid provides H+ in solution, so you have to be dissolved in water. Then let's go down to some of our other common gases. Carbon monoxide, anybody know anything about that gas? It's bad news. He is one tough customer. Carbon monoxide is produced by combustion reactions that do not get enough oxygen, and it actually can happen fairly quickly. So small doses, carbon monoxide poisoning will give you a headache. Large doses, you'll just fall asleep and you won't know what hit you. So that's why you're supposed to make sure all your combustion reactions have plenty of oxygen, so they produce carbon dioxide instead of carbon monoxide. I wonder oftentimes, like, how many times it happens by accident. So you come home from the grocery store, you pull into your garage, you got all these groceries in your car, and you say, wow, it's cold out. I think I'm going to close the garage door. Make sure you shut your car off first, because it does happen fairly quickly. And that's why you're supposed to have your furnace professionally checked, and also, believe it or not, your clothes dryer. Does anybody have a fireplace in here? Yeah, you got to watch out for those too. Those should be professionally cleaned, because if you get some squirrels or birds making nests in there, that could also result in carbon monoxide being produced. Ammonia, super common cleaning. It is a gas at standard conditions, but it loves to dissolve in water. So that's why when you go to the store and you buy ammonia off the shelf, looks like it's a liquid. Ammonia is actually a gas, but it loves water. So it will dissolve easily, and that's what you're buying. Nitric oxide and nitrogen dioxide. Those are products along with sulfur dioxide. Those are products of combustion reactions, also from impurities in gasoline. So those are our pollution gases that dissolve in water. Who remembers what you get when those pollution gases dissolve in water? Acid rain. That's not good either, right? And then look at that guy tucked in the middle there, nitrous oxide. Anybody ever had nitrous? You'd probably get it at the dentist's office. They call it laughing gas too. It's an anesthetic, but they call it laughing gas. You get real chatty and real giggly. So, but it is an anesthetic. It is pretty good stuff, isn't it? So eventually you guys will probably all have that when you have your wisdom teeth taken out. They usually give you nitrous. So isn't it funny? Look at how similar in chemical compounds those appear to be. Nitrogen dioxide, nitrous oxide, and sulfur dioxide. I mean, nitric oxide, they're super similar in chemical formula, but very different properties, just like carbon dioxide and carbon monoxide. Okay, and then you got some other ones that are also hydrogen sulfide is a gas that they sometimes put into natural gas, because you guys know that the natural gas that you use to cook with your stove and stuff like that is odorless and colorless. They put that smell in there. They want it to smell icky so you don't accidentally bump it, the gas valve, and fill your house with gas. And that's the problem, is you just fall asleep and you don't even know what's going on. So they put the smell in there so that we don't end up killing ourselves. Thank goodness for such smart people around, right? Came years and years before us smart people. Okay, characteristics of gases. Gases assume the volume and shape of their containers. They're mostly the most compressible state of matter. So solids and liquids have a specific volume, whereas gases do not have a specific volume. They will mix evenly and completely when confined to the same container. So that's convenient for us, because you can walk into my room and be like, oh, geez, I hope Miss Boston has oxygen today. You know that there's going to be oxygen in any room that you go into to breathe, which is super important. And they're the lowest density of all of the states of matter. Okay, we're going to start with a unit that might be a little bit new to you. So we all know what volume is. Volume is the amount of space that a particular substance takes up. Volume in chemistry class is either going to be measured in liters or milliliters. So we don't use a lot of those goofy measurements. So in chemistry class, we're always going to be using the metric system. We also are familiar with, that was volume. We're also familiar with temperature, because we learned that in our thermochemistry unit. It's a little bit different in gas laws, is temperature has to be measured in Kelvin. Even Celsius is not good enough for gas laws. And then there's one that might be a little bit unfamiliar to you, and this is called pressure. So same thing with pressure. This is a picture of a barometer. Unfortunately, I don't even have a barometer in my class because they took it away from me, because barometers are usually made with mercury. The reason they're made with mercury is because mercury is the most dense liquid. So if you were to make a barometer with water, it would have to be, so typically a barometer is about 1 meter tall. It would have to be like 13 meters tall, which is too big for this classroom. So how a barometer works is it actually has a pool of mercury at the bottom. That pool of mercury is being pressed on with the same amount of force as we are. So what it does is it presses down on the mercury and it pushes it up the column. And at the top of the column, there's what we call a vacuum. Does anybody know what's in a vacuum? Nothing. So when you say the pressure outside is 760 millimeters of mercury or 76 centimeters of mercury, that comes from actually taking a ruler out and measuring the height of the column of mercury. The more pressure that's pressing down on it, the higher it will push it up in the tube and the higher the pressure will be. So pressure is the amount of force per particular area. So basically you can think of the atmosphere as a blanket of air that is pressing on all of us. And that's because of gravity. So that's why when you go up into the mountains, the pressure is lower. Our units of pressure. So let's relate it to physics. A Pascal is what's called a Newton meter squared. So a Newton is a kilogram meter per second squared. We typically use the units of atmospheres. 760 millimeters of mercury is equal to 76 centimeters of mercury, and that's equal to 760 torr. Those are like the English measurements, which you're going to still see all around. So you'll occasionally bump into millimeters of mercury. That's fine. Can't fight City Hall. Going to the metric system is apparently too difficult for this country. And 1 atmosphere is equal to 101,325 pascals. Usually the units we'll use here, just because that's a big number, is 101.325 kilopascals. Those are all the possibilities that you're going to see for pressure. You're going to run into all of those. So let's kind of check out that column of air that is above the Earth. You'll see at sea level, standard pressure is 1 atmosphere. You go up 4 miles, and it's half the pressure. So as you go up, the pressure decreases. Okay, so let's talk about Boyle's law. Boyle's law has to do with pressure and volume. So let's kind of think of a stupid memorization trick to remind ourselves what we're talking about with Boyle's law. So if you think of boils as in boiling water or something like that, that's ignoring temperature. What that means is it's keeping temperature constant. So Boyle's law is pressure and volume. When you see a graph that goes down like that, what that means is as pressure increases, volume decreases. This is called an inverse relationship. That means as one goes up, the other goes down. Inverse relationships are multiplied in formulas. So my formula becomes P1V1 equals P2V2. Anytime you have a formula where 2 variables are multiplied by each other, they're inversely related. As one of these changes, the other's going to change also at a constant rate. So here was one of our scientists. Actually, back then, they were chemists and stuff like that, but they were really studying balloons. And the reason why is this was so long ago, there weren't cars. And that was literally a mode of transportation was hot air balloons. So reminder, temperature must be in Kelvin. So the volume of a gas is directly related to the temperature of a gas, meaning that as temperature goes up, volume goes up. You might know this too if you've ever been at a children's party and it starts getting hotter in the afternoon, and you'll notice that the balloons start to pop. And that's because as the temperature of the gas inside the balloon goes up, so will the volume. Same thing with pressure. Pressure and temperature are directly related also. So as pressure goes up, temperature also goes up. So my formula becomes, here's my two formulas. V1 over T1 equals V2 over T2, or P1 over T1 equals P2 over T2. These are directly related. As one goes up, the other goes up. That's what it means to be directly related.
So are they both?
This one, this one is Charles's law. This one's Gay-Lussac's law. So let's talk real quick. Remember, temperature must be in Kelvin. Kelvin is simply Celsius plus 273. Here, I'll write our other one up here too, so you can see them next to each other. This means as one goes up, the other goes down. So let's talk real quick why it has to be in Kelvin. That's because in Kelvin, 0 is absolute 0. You see in these formulas, you guys know what happens when you try to divide by a 0, don't you? Becomes undefined. And really, since temperature is the measure of the speed of a molecule, it doesn't make sense to have a temperature of 0. That means that all molecular motion stopped. You guys remember what it's called when all molecular motion stops? Absolute 0, and we haven't gotten there yet. Really, we shouldn't be able to get there on this planet, because that would violate laws of thermodynamics. So make a note for yourself someplace. We definitely need to have all the temperatures in Kelvin. Our last one is Avogadro's law. That's Avogadro's our guy who talks about amounts. So Avogadro's law is V1 over N1 equals V2 over N2. Yep. Divided by is direct. So these guys are all directly related. Boyle's law with pressure and volume are inversely related. So let's see a little bit of a picture of what it looks like. If you increase the pressure, you are making it so the molecules have less space to move around, and therefore the volume decreases. If you lower the temperature, you're lowering the speed. So the molecules are moving slower, therefore they take up less space and the volume will be smaller. Increase the temperature, the particles start to move faster, they take up more space. If you increase the pressure, then the temperature will also go up. Yes. Moles. N is for moles. Okay, so also make note someplace when you see STP, if you remember when we did our stoichiometry unit, we had a relationship that 1 mole of gas, didn't matter what kind of gas it was, took up 22.4 liters at STP. If you remember, I said we'll learn what STP is later. This is later. So in order to use that 22.4 liters, you have to be at STP, which is called standard temperature and pressure. Standard temperature is 0 degrees Celsius or 273.15 K. We usually just use 273. Standard pressure is 1 atmosphere. So when I plug this all in, it's a constant. So my formula, if you combine all of these together, you get P and V on the top and N and T on the bottom. If I plug in my STP values, I get a constant. That constant is called the ideal gas law constant. The ideal gas law constant, if you rearrange it, you get PV equals nRT, which is our ideal gas law. So that formula is called the ideal gas law. The ideal gas law constant is not one you'll have to remember. It'll always be given to you. And that's 0.08. We usually use 0.08206 liters atmospheres per mole K. Now you guys are far enough along in chemistry where you understand, okay, she's using 22.4 liters instead of 22.414 liters. Those are the same numbers. The only difference that they have is the amount of sig figs. So it's okay. They mean the same thing. It's just how many sig figs do you want to use? So we usually use 22.4 liters for the volume. We use 273 K for the Kelvin temperature, and we usually use 0.08206. You might even see 0.0821. All of those mean the same thing. And my units on top are pressure and volume units, so it's liters times atmospheres. My units on the bottom are moles and K. Okay, that's as far as we're going today.